Hello and welcome to today's episode of Kitchen Physics. I'm your host, Amanda. I'm a CPA by day and a foodie by night, and here I am doing fascinating physics in my kitchen. Let's get started. Today's physics experiment involves both Newton's second law and the energy principle. I used Newton's second law to predict the motion of a mass swinging from a spring. I also used the energy principle to find out more about the various energies involved in my spring mass system. I was able to program the computer to predict the motion of the mass, which oscillated in both the x and y dimensions. I was also able to show that, while a spring mass system is in motion, the various components of the system's energy will vary, but the total energy of the system will not. Newton's second law tells us that the motion of an object can be predicted by calculating the effects of the various forces acting on the object. I used the tracker video that we were provided. I calibrated it as we were shown in the video by using 0.7 meters as the length of the stretched spring with the mass hanging from it. I'm not sure this was completely accurate for this lab setup, but more about that later. I selected the origin as the attachment point of the spring, the positive x-axis to the right, and the positive y-axis to the top. I then tracked the motion of the mass frame by frame. Please note that for this part of the analysis, the system was selected to be the mass alone. I set up the computer program as we have done in previous labs. I started with the initial values of the variables. I used the mass that was given in the lab video and set the initial position of the object to its position in the first screen of the tracker video, or in other words, to the first experimental data point. I initialized the variable for the gravitational force near the surface of the Earth, and the variables for the spring stiffness constant and relaxed length of the spring as given in the lab video. I then set up the calculation loop to calculate the various forces acting on the mass as it is swinging. The first force is the gravitational force, which acts in the minus y dimension. The second force is the spring force, which acts in both the x and y dimensions depending on the position of the mass. The net force is the sum of the two, and this result is used to update the predicted motion of the mass. The predicted motion of the spring is then updated to provide correct beginning values for the next loop in the calculation of the spring force. As you can see, the mass represented by the blue ball oscillates in both the x and y directions. The black arrow represents the gravitational force, which points in the negative y direction. The blue arrow represents the spring force, which points in the direction of the spring. The yellow arrow represents the net force. For the next part of the analysis, I used the energy principle. For this analysis, the system was selected to be the mass, the spring, and the Earth. This meant that there were three different energies included in the system: the kinetic energy related to the motion, the potential energy related to the spring, and the potential energy related to gravitation. I calculated the initial values for each of those energies and then calculated the changes in each of the energies as the system's motion continued. I plotted the energies in a graph window, which showed, as expected, the individual potential energies and the kinetic energy oscillating, but the total energy of the system, represented by the yellow line, remaining the same through the prediction. Thus, the energy principle was satisfied by the predicted motion of the object. To compare the experimental data to the modeled predictions, I added a red ball to the display to represent the actual data. The red experimental ball is jerkier than the blue modeled ball due to the number of experimental points. It doesn't track terribly, but it's not great. I also created a second graph to compare y-coordinates in the experimental results to the predicted y-coordinates. In the graph, you can see that the periods of the oscillation are about the same, but that the red experimental line is significantly below the blue modeled line, especially at the lowest points. I believe this is because the calibration in the video was not especially accurate. The video we were given never actually showed the mass hanging still, so that I was just guessing where to put the 0.7 meter calibration stick. What does it mean? As previously stated, the computer model predicted that, for this experiment, the energy principle was satisfied. The total energy of the system, represented by the yellow line on the graph, did not change. What else does it mean? I estimated the oscillation periods from the X data I collected in the tracker video and from the Y data I collected in the tracker video. The average period for the X data was 1.65 seconds, and for the Y data it was 1.52 seconds. They should be the same, but they are pretty close, and I believe the minor differences resulted from inaccuracies in my video tracking. As for springs in the kitchen, you don't need to pay a bunch of money for chip clips to keep your snacks crispy and keep critters out. Just get some clothespins, the old school kind, with a spring. Thanks for watching, and I'll see you next time on Kitchen Physics.